Welcome to the first video of section 4.3 on the method of Lagrange multipliers. The goal of this section is to use Lagrange multipliers to find absolute extrema when they exist for functions of several variables given constraints. Subsection 4.3.1, one constraint. Theorem 4.3.1. Let f of xy and g of xy have continuous partial derivatives in some open set containing the smooth curve g of xy is equal to k for some k in R. If f has a local extrema at ab, when restricted to the curve g of xy is equal to k, and if the gradient of ab is not equal to 0, the gradient of g at ab is not equal to 0, then there is some real number lambda such that the gradient of f at ab is equal to lambda times the gradient of g at ab. A couple of remarks before we unpack this theorem and give some justifications. First remark, in this context, the curve g of xy is equal to k is often called a constraint. Typically, we would say that we want to maximize or minimize f subject to the constraint g of xy is equal to k. The real number lambda, this one here, is what is called a Lagrange multiplier. Justification. So let's unpack this theorem and see what it's really talking about. So first of all, let's imagine that we have a function f of xy that we want to maximize. So I'm going to draw a function that we've seen a shape of before. So let's draw this function as a upward facing paraboloid. Give ourselves some axes here. And let's imagine that we have a constraint curve. So a constraint curve, you'll notice, so if this is our function f of xy, then it is a 3D, it's a surface in 3 dimensions. If we take another function g of xy and we set it equal to k, then we get what we could interpret as a level curve of g of xy, which is a curve down in the xy plane. So let's imagine that we had one here. Something like this, maybe. So this is our curve g of xy is equal to k. If we're going to restrict f, to this curve g of xy, that means we're looking at the image of this curve up on the surface. We're looking at the values of f when taken on this curve only. So let's imagine that the curve maps up, so that if we take all of these points and take the images up, we can draw the curve on the surface. Now the way I've drawn it, we have a couple of extrema here. Let's look at this one. So this extreme value, it's on a level curve of f as well. So there's a level curve of f that extreme value is on, and we can imagine projecting that level curve of f down onto the xy plane as well. And the insight here is that when f has a maximum value on some restricted curve, then its maximum value and the level curve are going to share a tangent line. The image of the constraint curve and the level curve will be tangent to each other. You should be able to see that from the diagram that I've drawn there. Now my diagram here is a little bit busy. Let's take this and redraw the axes flat in R2 so we can get a real handle on what's going on. So there's x and there's y. Let's add the level curve in. That's pretty good. And then the constraint curve might look something like this. And our tangent line is kind of here. So we had said that we can interpret g of xy equals k as a level curve of a surface g. Well then the gradient, what do we know about the gradient? Gradients are always perpendicular to level curves. So that means at any point on the surface, on the level curve of g, where I draw the gradient, it would be perpendicular to the curve g of xy equals k. Similarly, if I drew the gradient of f, well, it would be perpendicular to its level curve. So what happens at this point then when the two curves, the level curve on f and the constraint curve, are tangent? Well, the gradient of each has to be perpendicular to the level curve. If the level curves are tangent, then the gradient of f and the gradient of g are perpendicular to the same thing. And as long as neither is 0, then they are parallel. Well, depending on your definition of parallel, it could be when they're 0 as well. But we have f parallel to the gradient of g. And if they are parallel, then they are scalar multiples. So that is sort of a geometric visualization of what's happening, where we come up with this equation that the gradient of f must be a multiple of the gradient of g at some point. I guess I should call this AB. At a point AB where f has a maximum or a minimum when restricted to input values that are on the curve. In the next video, we're going to see a little bit more of an algebraic justification as to why this formula makes sense.